Hello. In 8.3, what we're going to do is explore integrals further. We're going to look at the special case where you have powers of trig functions and product of trig functions. So the first thing we're going to look at is powers of sine and powers of cosine. So if you have odd powers of either sine or cosine, what you'd like to do is save one factor. If it's sine, you just save one factor of sine and then rewrite the remaining factors, because those factors will be even powers, as cosine, using the identity that sine squared is equal to 1 minus cosine squared. Okay. Or if you're looking at integrating powers of cosine, then you would save one factor of cosine, write the remaining even powers of cosine as 1 minus sine squared. So you're then going to use a u substitution of cosine. And the reason why is that, remember, you reserved one factor of sine. If u is cosine, then the derivative is going to be negative sine. So that means that factor of sine dx will be replaced by your du. Okay. If you have even powers of sine or cosine, then you're going to use the half angle formulas, or also called the reducing power formula, to replace all the even powers with 1/2 1 minus cosine of 2x. Or if you have even powers of cosine squared, you're going to replace each of those with 1/2 1 plus cosine of 2x. So let's just go ahead and look at example 1. We're going to evaluate the integral of cosine to the 4th, and we have a problem with that because our typical techniques won't work, because it's like cosine times cosine times cosine times cosine. So this is actually a product of functions of x. So what we're going to do is we're going to break this up into cosine squared times cosine squared dx. And then we can replace each of the cosine squares with 1/2 times 1 plus cosine of 2x. So times 1/2 1 plus cosine of 2x. The idea is to keep reducing the powers so that we eventually get something that we can integrate. And now what I'm going to do is I'm going to just take out the 1/2 times 1/2 into the front of my integral. There's going to be a lot of algebra here. To get 1/4 the integral of, and now I can also multiply these two pieces, the 1 plus cosine 2x times 1 plus cosine 2x, and get rid of those parentheses. So our integrand will be 1 plus, and I have 2 of those cosine of 2x plus cosine squared 2x dx. All right. And we shall keep going. I have a problem though. I know how to integrate the 1 and the 2 cosine 2x, but I still have this cosine squared 2x that I don't know what to do with. So I'm going to use that lowering power again. So it's 1/4 the integral of 1 plus 2 cosine of 2x plus 1/2 1 plus cosine, and now remember we're doubling the argument. So here my argument is 2x, so it's going to be cosine of 4x dx. So this is a little bit tedious, but the goal again is to get rid of all the cosine squares. Now I'm going to distribute the 1/2 and get rid of the parentheses to get the integral of 1 plus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x dx. So if you notice we have some like terms, I can take 1 plus 1/2 and get 3/2. So 1/4 integral of 3/2 plus 2 cosine of 2x plus 1/2 cosine of 4x and dx. So if you want to go ahead and clear the fractions by factoring out a 1/2, you can, but I'm not going to. I'm just going to integrate it as it's written. So the integral will be 1/4 times 3 over 2x plus, and then recall that cosine is going to be sine, right? The argument will stay the same. So it's sine of 2x, but we have to divide by 2. So the 2's are going to end up canceling, and I'll end up with sine of 2x. And then cosine of 4x is sine of 4x times 1/4. So this actually ends up being 1 over 8 plus 1 over 8 cosine, oops, sorry, not cosine, sine of 4x. And that's going to be plus our constant c. So you could factor something out, or you could just multiply through by the 1/4 to get rid of the brackets, and I think that's what I'm going to do. So I'm going to get 3 over 8 x plus 1/4 sine of 2x plus 1 over 32 sine of 4x, and then plus my constant c. Okay, so again, it's a little bit tedious, and you just have to be careful with your computations, but the idea is just to keep breaking it down until you get something that you can integrate. So let's look at another example. In example 2, we're going to be evaluating sine to the 3rd power. So we can't use the lowering powers or that half angle formula. What we want to do is pull out one factor. Since it's an odd power, it's 3. We're going to pull out one factor of sine. So this becomes the integral of sine squared x times sine of x dx. So the reason we're going to do that is because then we can go ahead and replace sine squared with 1 minus cosine squared. Oops. And of course I forgot my x here, my dx. So what we're going to do is write the integral of 1 minus cosine squared x. And we have this sine of x dx, which will go away if I do a u substitution of cosine. So if I let u equal cosine of x, that means that in the parentheses, this will be 1 minus u squared. And also, my du is going to be negative sine of x dx, right? Which is just negative du is sine of x dx. I don't know why I keep forgetting my x. So that means I can replace sine of x dx with negative du. So I'll get the integral of 1 minus u squared, okay, times negative du. And you could pull out that negative in front of the du, but also something nice from algebra, if I take the negative and I multiply the 1 minus u squared, I'll just be changing the order to u squared minus 1, and then our du. When I integrate, this is going to be u to the third over 3 minus u, plus our constant c. So again, we have to substitute back in for u, and u is just cosine. So we get cosine cubed of x over 3 minus cosine of x plus our constant c. And that's where you can stop. You don't need to combine the cosine cubed of x over 3 minus cosine of x. So there is a nice formula in this section here, which we could have used for the last two examples, and this is our reduction formulas. They're kind of tedious because you may have to do it repeated times. It just depends on what the power is, okay? So if your n is really large, then what you're going to end up with is an integral that still has, say, well, let's just say n is equal to 4. So you'll have sine of 2, right? Sine squared, and you'll still have to reduce that. But then you can use the reduction formula again. So you are allowed to use these over and over again until you get something that you can integrate. So what we're going to do now is we're going to look at what happens when we have products of sine and cosine. So let's say that the exponent on sine, this m value, is odd. Okay, so what we're going to do is what we did before when we had an odd power. We're going to save one factor of sine. Okay, so then think about that. The remaining factors of sine will be even, and we can replace them with 1 minus cosine squared. So in the integrand, I'll have one factor of sine, but then I'll have cosine, and I'll have 1 minus cosine squared. So everything will be written in terms of cosine except that one factor of sine that I pulled out. But then when we do our u substitution of cosine of x, then we'll have our sine of dx cancel, right, and be replaced with a du. If it turns out that the exponent n on cosine is odd, then you're just going to be saving one factor of cosine. The remaining factors will be even, and you can replace them all with 1 minus sine squared. So your u is going to be sine. That way your integral can be written in terms of only sine, right? And then that one factor of cosine that you pulled out will go away, because that will become your du. Now, even powers, that's a little bit different because both m and n have to both be even. And then what you're going to be doing is, and again, this is super tedious, is you're going to be using the identities here to just reduce the powers and keep reducing the powers until it's something that you can integrate. Now, I would never give you something long like that on an exam. That's just way, it's too much of a waste of your time, actually. So let's just look at an example. We have sine to the fourth and cosine to the fifth. So they're not both even. One is even and one is odd. And cosine is the one with the odd power. So what I'm going to do is, since cosine is the one with the odd power, I'm going to reserve one factor of cosine. And my integral will be sine to the fourth times x cosine to the 4th times x times cosine of x dx. All right, so I'm going to replace the remaining even powers of cosine with 1 minus sine squared. So if you want to write this out as cosine squared times cosine squared, that's fine. But really that's the same as 1 minus cosine squared x quantity squared. It says the exact same thing. Did I just write cosine squared? Oops, I don't know where my mind is at today. It is 1 minus sine squared x quantity squared. Apologies. Okay, so now our u substitution will be sine, and then our derivative is going to be cosine of x dx. And now we can replace the cosine of x dx with du, and then we can replace all of our sines with u, and everything will be written in terms of u. So this is going to be u to the 4th, 1 minus u squared squared du. So this is basically just a polynomial. We can go ahead and multiply all of this out. Here, the 1 minus u squared squared would turn into 1 minus 2u squared plus u to the 4th. And then distributing the u to the 4th, I have u to the 4th minus 2u to the 6th plus u to the 8th. So the antiderivative here is going to be u to the 5th over 5 minus 2u to the 7 over 7 plus u to the 9 over 9, and then plus our constant c. So last step would be to substitute the sign for the u. So we'll have sine to the 5th over 5 minus 2 sine to the 7th over 7 plus sine to the 9th over 9 plus our constant c. And we are done. So let's go on next page, and what we're going to discuss now is we're going to discuss products of tangent and secant. So the idea is going to be similar to what we did before. Okay? We want to choose our u substitution wisely so that we can eventually write everything in terms of u. So now if our n is even, meaning the exponent on secant, this time we're going to save one factor of actually secant squared, because remember, if we take the derivative of tangent, it's secant squared. So we're going to reserve secant squared, and we're going to change the remaining factors of secant using the identity that secant squared is 1 plus tangent squared. So that means our integrand is going to be all in terms of tangent. Our u substitution is tangent. And then when we take the derivative of tangent, we get that secant squared dx that we can get rid of. Now, if the exponent on tangent is odd, then you're going to save one factor of secant tangent. Change the remaining tangent factors. Since it's odd and we had one tangent that we pulled out, we're going to change the remaining factors using the identity that tangent squared is equal to secant squared minus 1. So our u substitution will be secant, because the derivative of secant is secant tangent, which will become du. Okay. And this is the only cases that work here for a product of tangent secant. If it doesn't fit criteria 1 or 2, you have to do 3. You have to do other techniques. So now when we look at our example 4, I see that the exponent on secant is even, right? So this fits that criteria 1. But also look, this is tangent to the power of 1. So it also fits criteria 2 as well. So I could use either one of these. I'm going to go ahead and use 1. I'm going to reserve 1 factor of secant squared. So this becomes secant squared times tangent times secant squared dx. And then I'm going to replace my secant squared with the identity so that everything's in terms of tangent. So this is going to be 1 plus tangent squared times tangent. And then I have this secant squared x dx that I need to get rid of by letting u be tangent. So my du is secant squared x dx. Okay. So once I replace the secant squared x dx with du and replace all the tangents with u, I will have an integral with just the variable u. So we have 1 plus u squared times u times du. And then distributing the u and getting rid of the parentheses, I have u plus u to the third du, which is super easy to integrate. Okay. I get u squared over 2 plus u to the fourth over 4 plus our constant c. And then I can replace the u with tangent. So tangent squared over 2 plus tangent to the fourth over 4 plus c. And that's it. So let's go ahead and look at the following page. And we're not going to do any computations here, just going to discuss this. Okay. If we look at the cotangent cosecant rules, they're exactly the same as the rules for tangent secant. Okay. It's the same idea. So we're really not going to be doing an example with that. You would just follow the same example that I did in the previous one, except for you just have cotangent cosecant instead of tangent secant. But something that's really nice is theorem 8.1. We didn't have this before, but now we actually have these integrals for tangent, cotangent, secant, and cosecant. So you're free to use these as well. Now remember, on the next exam, you're going to be allowed to bring in a page of notes. So hopefully you will include a lot of this stuff on there. Okay, so that's it for 8.3, and I'm done.